coming. So today I'm going to be talking to you about my work with laser scanning technology and using coral skeletons to try and quantify coral morphology. Now, apologies in advance if any of you made it to my talk at ICRS. This is going to be a little bit more of the same, but I will be doing a live demonstration to hopefully spice things up, providing that it actually works. So, being the Centre for Excellence for Coral Reef Studies, I assume most of you have at least heard of what scleractinian coral is. So some of us that will mean things like acropora or asclepiora, and to others it might mean things like slimy photosynthetic rocks, which I've heard some really fish biologists mention them to be. So what I'm basically interested in, regardless of your own personal views on corals, they are, as you can imagine, really important for a coral reef, and they provide a whole range of different functions on the reef, from building the reef and consolidating the reef substrate to providing habitat for secondary biodiversity. And so the main thrust of my... Hang on. Oh, I've skipped something. Okay. Oh no, sorry, that is coming up later. We will see how this goes. So basically what I'm interested in, and the main thrust of my PhD, is looking at coral community structure and trying to work out if the characteristics of corals can help drive and sort of provide a mechanistic link to driving coral community structure. And it was working with corals, and I was thinking about coral morphology in particular, based on the fact that they're very variable. So there's a wide range of morphologies that corals can take. And so usually corals are broken down into different categories, so such as massive, branching, and corymbose, those sorts of things. And these are really useful when it comes to being out on the reef and doing things like species identification, or for going up for different, for other general ideas such as the distribution of corals through a depth gradient, or their response to an external factor such as their likelihood of dislodgement during a storm. But I wanted to, and so I was looking at coral traits and particularly trying to concentrate on morphology, and realised that I needed to sort of come up with a bit more of a robust approach and sort of actually getting a quantitative handle on morphology to move forward. And so that's where I asked the question of, can coral morphology be reduced to a few major axes of variation within a quantitative framework? Can we come up with a few morphological traits that really capture and describe the majority of the variation within a coral growth, within coral morphology? And so when looking at, when you think about corals and thinking about quantifying corals, some of them are much easier to work with, such as this goniastria here. Kind of sort of looks like a nice round boulder, quite regular looking. But some of them become slightly more elaborate, such as this digitate colony here, and then others, I think you'll agree, are just kind of showing off a bit, such as this acropora laricus. But what you can do is you can take these sort of general categories and align them in a sort of rough axis of increasing spatial complexity. And along with that comes ideas of other things, such as increasing surface area to volume ratios. Now, for corals, we think this is quite important because, generally speaking, the majority of the biomass is associated with the surface of the coral skeleton, and the majority of the volume is occupied by an energetically expensive to produce skeleton. So you can imagine if you're able to maximise your biomass per unit investment in skeleton, you might be able to have a competitive advantage over others. However, this also comes at a cost, for example, increased likelihood of bleaching and storm damage. And so that's something that we're quite interested in looking at. So what you can do for some of the simpler species is you can estimate this. So for the massive species, you can say, look at a hemisphere, let's just calculate surface area to volume for a hemisphere and approximate it like that. But when you start trying to come up with more complex geometry, such as for the digitate colonies, it becomes increasingly difficult. And at some point, you basically have to give up and just go out there and actually try and measure them. And so that's what I was interested in doing. Now, I'm not the first person to think about coral morphology, far from it. There are a whole range of really fantastic publications and methodologies being developed that have used everything from sort of manual measuring of linear extension rates to really high-tech solutions such as CT scanning technology. And recently there's been a bit of a renaissance of using photogrammetry and image analysis software, using things such as ImageJ. And so associated with these methods is a range of trade-offs, including things like cost, portability, accuracy, and processing time. And so I was kind of thinking about what is the best of both worlds here. How can I sort of get a quantitative handle without having to, convince a hospital to let me use their CT scanner, for example? And I came across the idea of using portable laser scanning technology as a potential shoe-in for this. Now, I must say that while a portable laser scanner is much cheaper than a CT scanner, it's still way above the budget of my PhD equipment budget, basically by about a factor of 10. But thankfully I managed to get in contact with one of the manufacturers of these scanners and convince them somehow to let me have one for free for a period of 12 months, and that's what I've been working with now. So what I'll do is I'll move on to the second part of this, where I will hopefully, technology permitting, do a live demonstration. So what I'll quickly do here is just switch over, if I can remember how to use this. This is looking promising. Presentation. And there we go. So, there we go. So, some of you at the front might have already spotted this, but from the back, here we go. This is the Careerform Exoscan laser scanner. And it basically looks a lot like a ray gun and is operated by a trigger, so I don't tend to take this out in public too much because people get invested. But it's a very simple unit, to be honest. At the top, you've got 3 cameras here, which are all which are all paired together. And these can basically image both the reflected targets down there as well as the laser cross that we projected from the bottom here. And all you simply do is attach it to a laptop, which we've got here, via a data cable, and you can see up here the software that comes with the scanner for the scanning process. And so it comes into 2 phases when you're trying to set up a scan. So some of you see at the back, there's all these reflected targets here. And so basically the scanner and the hardware knows the exact dimensions of these reflected markers. And so depending on how close or far away it gets, it can keep position of itself in 3-dimensional space. And so the first thing you want to do is develop a positioning model by scanning these targets. And you can place these on or around the object that you're looking to scan. So if it's a car, you can place the targets on the car and go along like that. But what I tend to do is sort of set out a situation here, and then sort of place my object in the scanning environment. So what I'll do now is just quickly show you how easy it is to develop a positioning model. You literally point and shoot, and you should see, and if I go down like that, you can see how it keeps position of itself in 3-dimensional space. And so that's the first step. And so what I'll do is I'll stuck that down. And then the next thing you do is just quickly optimize the positioning model. It's just a sort of box you have to tick. And then also what I don't want to do is scan the table, because one, it doesn't look as good when you're trying to do a presentation, and it also wastes computing power. So what I'll do here, I just set the scanning resolution to 0.5 millimeters. And here, and so what I do is I pick 3 of these targets here, and that comes up with a parallel plane, which you'll see here. And then I just basically move this plane a few millimeters away from the surface of the table, which you can see there, and basically anything below that, it doesn't bother scanning. And so that's just, it's really quite handy in this case. And then you're basically ready to go to scan. So what I'll do is I'll just set out a few bits and pieces here. Just set that there, and you're pretty much ready to go. So you just press start, and then you take your coral skeleton. So Andrew Baird has kindly donated one of his own here for me to scan. So you just place it in the centre of the scanning environment. What I'll also do, so it's easy to see, it's like the zoom. And then again, it's just point and shoot. So you should be able to see, let's do quickly, you get this 3-dimensional model, this 3-dimensional surface starting to build up. And the way that this works is the same way that the 2 cameras can keep track of their position by using reflected markers. When it knows its position in space and then projects that laser cross, it can tell based on the shape of the cross and how it changes depending on the surface that it hits. Basically, it can tell how far away the laser is, and it records that as a set of 3-dimensional coordinates. And so what I'm doing here is I'm scanning at a resolution of 0.5 millimeters squared, but it goes up to 0.2 millimeters squared, which is really high resolution. One of the downsides of using the highest resolution is that for every time you increase your accuracy by a factor of 2, things like processing power and the file size increases by a factor of 4, so it does start to get pretty crazy pretty quick. And what you can do, provided I don't mess this up, is very carefully rotate it there, so that way you don't have to see my back when I'm scanning it to the next side. You can rotate them, as long as the object doesn't move and the reflecting markers stay in position, you can sort of do a rotation here and then continue to scan. So I'm not sure exactly how long this is going to take, as I usually scan one of the massives, which goes very, very quickly. So if any of you guys have any questions, feel free to shout.
It says 7% at 7.5 gig. Is the 7.5 gig determined by the resolution that you set?
The 7.5 gig is the RAM on the laptop. So if you've got more RAM, you can scan more at once. But what you can do, and what I will do here, well, what I usually do is, so as you can see, I'm scanning this side here. And what I usually do is I then flip it on its back basically and scan it again. And the software allows you to merge the two halves of the scan basically together to sort of create this full 3-dimensional surface, which I'll show you in just a sec. So I'll just try and get a few more bits in. Actually, that. Any other questions at all?
What sort of grunt do you need to drive it? on the CPU side of it? Just a
I
ordinary laptop?
think it's just a sort of an older version than I think of this, but yeah.
Just an ordinary laptop?
Yeah, just an ordinary laptop. Yeah. So they provided this. Actually, my own personal laptop is more powerful, but this model requires a firewire connection, I think, or wire connection. So anyway, and you can see it sort of builds up this three-dimensional surface really rapidly. So if you can imagine if you want to do this with a CT scanner, of course the CT scanner is fantastic because it allows you to get the internal structures as well. But this allows you to get an idea of the general morphology really quite rapidly. And I think it allows you to do what I've done and now scan up to about 250 coral skeletons since I've had this unit. So this isn't perfect at the moment. If I had more time, I would go through and scan this a bit properly. But what you can see is you can actually see the coral-like detail coming out there. So it's pretty impressive. And again, once you actually go through and scan this completely, flip it upside down, and merge the two scans, you'll end up with a full three-dimensional model. And so what I'll do now is show you some of these models. I'll just load them up here, and so you can get an idea of the sort of the range of different shapes and sizes that you can actually get. So what I'll do. And so you can imagine something like your Graniastria here. You've got it kind of looks a bit like a squash golf ball, but you can sort of see the coral-like detail up there. And again, this isn't even the highest resolution this scanner allows you to go, which is really quite impressive, at least in my mind. And then you can look at something much larger, for example. So this is a turbinaria bifrons that I've managed to wrangle out of a cupboard. I'm not sure if you can see at the bottom there the scale. So this is actually probably about 70, 80 centimeters wide, quite long. And you can sort of see, you get right down in there into the detail, you get these fronds, and then when you flip it upside down, you get some of the more sort of rugged and rugose textures along the bottom as well. So it's really quite impressive and handy for this sort of work. And then of course you can have a look at things like this section of the proper intermedia here. You see all the different branching patterns and the gaps between the branches are getting covered quite well. And then for something like a millipora here, you can see it really does pick up the detail in quite a useful and very fine manner. But this is not to say this is without its drawbacks. So as I mentioned, the camera requires both cameras need to see the laser cross at the same time. So in this case, for something like a table coral where they have lots of small branches that are okay there. That will help. There we go. Okay, so what we have here is a section of a table coral, a Coprolhyacinthus. And the problem is that if you can imagine scanning your hand, both cameras need to see the laser cross at the same time. So what it tends to do is it records the fingertips and it records the bases, the space in between the branches, and this is because of this occlusion that occurs. And so you might look at this and think, well, that's not really, it's okay, but there's all these holes everywhere. And if you want to calculate something like volume, you need to sort of, actually create a full mesh. But what the software allows you to do is to basically interpolate where that missing data is. So it's important that it doesn't record data unless it's sure of the data. So the data you record is accurate. And what you can then do is allow either use an automatic process, which sometimes works, or you can do what I tend to have to do with these sort of guys, and what you can do is you can basically create a scaffold. So what you can see, if we zoom into this section here, is, okay, we've missed this section, but we know that these two parts, and if you use reference photos as well, these two parts should join up. And so what you do is you simply click here and create a bridge. So you just click these parts there, click these parts there. And it's very easy to pick up and to get an understanding for it, and that will go there. And you just go around and do that depending on how patient you are and how big the specimen is, and you can do that and keep trying until you get the full model. And so what you end up with is something that looks like this. So you do lose some of the surface detail, unfortunately, when you go through this process, but the general morphology is still kept pretty well. So what we wanted to do to validate this is we want to compare it to something that's really highly accurate, so CT scale meshes. And so what you can see here is the same skeleton, but put through a CT scanner, and you can see it kind of is really, it's pretty impressive when you can see the sort of outputs you get from the CT scans. And I'm not going to be able to do this because of the resolution. Basically, what I'll describe now is, what I would have shown you visually, is basically what you can then do is take the CT scan data and you align the laser scan data in the software. And what it will do is create a color map. So you can set the parameters and say everything in green is within 0.5 millimeters positive or negative from the reference, which would be the CT scan. And then anything in the red would be anything negatively deviating, anything in the blue would be positively deviating. So you can sort of find out where your localized differences are between these two methods, and you see if any of the branches for some reason disappear, which they tend to do, I don't know why. Sometimes they disappear, and you can sort of pick that up and go back and have a look. And so, okay, I've just described I was going to show something nice and colourful and pretty, but I'm sure many of you here will be interested in seeing some data. Where are your error bars? Where are your actual data points? So I'm now going to switch back to the presentation. Okay, and so what we did here was we basically calculated some morphological traits such as surface area and volume from both the laser scans and the CT scan data. And so what you'll see here on the y-axis will be the data that we gathered from the laser scan meshes, and on the x-axis will be the data that we gathered from the CT scan meshes. Now, the more in agreement this data are, the closer they'll be to this sort of 1-1 line that you'll be able to see there. Now, I should mention that this data is somewhat outdated from about December last year, actually. I've had a lot going on. So there are about 9 data points here, which cover a range of different growth forms. And actually, with the processing of the laser scan models, we'd expect that the data would more or less be close to this 1-1 line. However, even at this very rudimentary level, when you look at the values that you get from volume, you can see that it's slightly, the laser scanner slightly overestimates volume, but nothing. I think I'd be quite happy to use this moving forward. And then when you look at surface area, it tends to underestimate. But again, this is because when you use the waterside remesh tool, when you sort of interpret that missing data, you lose some surface detail, and obviously any miss in rugrosity of the surface is going to cause a reduction in the surface area that you actually calculate. And then so when you look at surface area volume ratios, this is the data that we've got there. So we basically had the laser scanner, and I had some validation that the methods in the actual laser scanner works. And so the next step was to basically find someone that had lots of corals, and the Natural History Museum in London had tens of thousands of corals. And so I got in contact with these guys and said, "It's a really cool laser scanner, you guys have got some corals, let's make something happen." And obviously a much more formal tone in the email there. And they thankfully said yes, and so I worked there for about a period of 3 months earlier this year. I didn't actually work here. I worked at the slightly less glamorous but no less interesting site of Wandsworth, which looks like this. But this is actually a really interesting place because not many people go here, and there were some really cool things that I found in cupboards and stuff like this, such as there were trays of Darwin's barnacles actually from his monograph that were actually there. It's really quite cool to see. And so when I was there, I scanned around about 150 specimens, but the data I'll be showing you now comes from 111 scanned specimens. This covers 5 growth forms and 11 species. And so we've tried to cover a whole range of different colony sizes as well within these subsets. And so the data that I'll be showing you today in the growth forms are the massives, which kind of look like little swashbucklers, the digitates, or projecting up finger type projections, arborescents, so like open branching type things, tables, which as you can imagine look a little bit like a table, and the corymbose, which to be honest I'm not really sure what corymbose is, but that's what they look like. So the data that again I'll be showing you will be primarily surface area and volume ratio. So again, like I said, we believe surface area and volume and the interaction between these two is likely to be important for biology and the ecology of corals. And so what we have here on the y-axis is surface area, and on the x-axis is volume, and they're both being log transformed to make the lower values easier to see. It basically linearizes the data. And what we also do is calculate these values for a range of different hemispheres to use as like an anchor and a way to sort of compare the rest of the data to. So we've got some comparison there. And as you might be able to imagine with the massives, they do line up pretty well to this sort of hemispherical assumption, which is really good if you've been using that in your previous research. This means that you've done the right thing. But when you have a look at things like the digitate colonies, we can see is this sort of stratification coming out between both the stratification of surface area volume ratio coming out between them. So for the same volume of skeleton for the massives in the digitate colonies, you've got more surface area. And you can see at the start, they basically, I should work out to use the laser pointer. There we go. And so you can see at the start, they basically are quite in agreement. There's not much difference, but it starts to diverge as colony size increases. And then when you look at something like the arborescent colonies, it's not as dramatic a departure, but still consistently across the whole range of colony volumes that we've scanned with the colony sizes, there's still this higher surface area to volume ratio. So this is biologically important and biologically relevant for the organism as we expect it to be. that you can begin to think about how, even in a general sense, you can now, in a very quantitative way, say we know that digitate colonies have a higher surface area to volume ratio, and how that can feed into the research questions that you'd like to ask. But then things get interesting when you look at things like the tables and the corymbose colonies. You see that actually the picture becomes a bit more muddled. So these three colonies, I would have thought personally that the corymbose would have had the higher surface area to volume ratio by quite a fair bit. But here you can see that all three of these are actually in pretty much agreement. Now again, if surface area to volume ratios are important biologically and ecologically, then you can say that these three very different growth forms, just by looking at them, you can tell they're very morphologically different. But in terms of surface area to volume ratios, they're still very quite similar. And so something else I wanted to look into was not just the surface area in total, but basically how this surface area or this biomass is distributed through space. And so what I did here was I basically took a colony and had height 0 as the attachment point, and going up through in a planar way up through the water column, had a look at how surface area is distributed. And so the way that I did this, if you think about a three-dimensional mesh, it's basically a load of x, y, z coordinates in space, which you draw triangles between, and then that's how you calculate your surface area. So as long as you have a sort of, the resolution is consistent, the space between the points is consistent throughout your entire mesh, you could then convert it to a point cloud, and then you can then, between say the height of 0 and 1, count those points, and they're a good proxy for surface area. And again, surface area relates to things like biomass, and so you can start to see how biomass is distributed through a vertical plane. And so this is what we have here. So on the y-axis we have height above the substrate in millimeters, and then we literally have the frequency of the x, y, z coordinates from the point mesh. And so if you have a look for the massives, I'm sure if I asked you to draw this, this is the sort of thing you might be able to come up with yourself. It's kind of, they're more or less evenly distributed. The majority of them are towards the bottom, and there's a slight taper off, but nothing, more or less evenly distributed through this vertical plane. When you look at an arborescent colony, you actually see something very different. So this is basically saying the majority of the biomass, maybe the majority of the polyps, is actually distributed more in the center of the colony height. And again, if there are biological and ecological advantages or disadvantages associated with this, you can now potentially, have this tool set when you're describing colony morphology to move forward. And then when you look at the corymbose colonies, it's even more pronounced. The vast majority here, at least for this specimen, is distributed way above from their attachment point. And so when you put these in a sort of, increasing surface area to volume ratio difference, for example, you can see that these differences seem quite pronounced. And another thing that's quite interesting as well is, if you remember, for the arborescents and the corymbose, when it comes to surface area to volume ratio, they were very similar. There wasn't much difference between the two. But here, if this holds true across in a very general sense, in a general sort of pattern, you can see that there's actually now this other way, this other axis of looking at morphology that we can start to see these differences coming out. And so it's my hope that this is a nice sort of springboard, and these are just two of many morphological traits I plan to look at and to get a quantitative handle on. But if you can imagine that if there is a general sort of, you could plot a general curve for the distribution of mass for massives, which always looks like that, and like a normal distribution vertically for, open branching colonies, you can start to get a good, you can increase your vocabulary basically that you have to describe these species. And so I guess in conclusion what I'd like to say is that laser scanning technology is an effective tool for quantifying colony morphology. And then even very preliminary analysis is showing real promise in using this three-dimensional data to move towards this quantitative framework of colony morphology. And for myself, the next step is to basically take these traits, take these morphological data, and then apply them to real-world questions of biology and ecology related to coral community structure. And these are some of the other ideas that I came up with, and I'm sure that many of you will have lots of ideas as well. And so I'd just like to take some time to say thank you for some acknowledgements. So my supervisors, Maria Donalaz and Josh Maiden, Creaform for the equipment, which has been amazing, Jenny House and Luke Goodell for the CT scan models for the data validation, and the Natural History Museum for hosting and specimen access. And I'd like to thank all of you for listening.